Hi everyone, welcome to our 7th and last episode in our statistics series. Today we'll grapple with various applications of the distributions we discovered throughout our series. So in this episode we'll be grappling with three topics. Number 1, the normal approximation to the binomial distribution. Number 2, the central limit theorem, which is the most misunderstood theorem in statistics. And finally, number 3, sample proportions, which is what we're more interested in real life. So, the binomial distribution being discrete can often at times be very clunky and hard to use. However, a normal distribution being continuous is smoother and a little more malleable to use in calculations. So, we can try to approximate the binomial distribution to the normal distribution and utilize all the properties and formulas of the normal distribution. The binomial distribution takes on all sorts of different shapes and sizes depending on the values of the two parameters n and p. A particular feature we like to observe is called skewness, which tells us where the tail of the distribution lies. So a right or positive skew has a long tail to the right or positive side of the probability distribution. Now, don't get confused because the peak is on the left. A right skew will occur when there is a low probability of success close to 0. This is why the peak is lower on the left, because it's likely that there will be a lower number of successes, and the tail is higher on the right because it's rarer to get a high number of successes. Similarly, a left or negative skew has a tail on the left or negative side of the PMF. Again, just note that the peak is on the right because a high probability of success, close to 1, will likely result in a higher score. A non-skewed distribution has no extreme tail on one side compared to the other, so it's more evenly spread and symmetrical like a normal distribution. A non-skewed distribution will occur when the probability of success is close to even or when you have a large number of trials n. So before we approximate, we just need to make sure that the binomial distribution looks at least similar to a nice bell curve. Let's consider our parameters. Firstly, the larger the number of trials, the more accurate the approximation. Secondly, non-extreme probabilities of P and Q are preferred so it won't be skewed as much. It's hard to quantify a perfect condition because it's just an approximation, but we can quantify two conditions that strikes a good balance, which is NP greater than 5 and NQ greater than 5. There will be other versions, but note that a larger n will always result in a better approximation. So once these two conditions are met, starting from the binomial distributions with parameters n and p, we can extract the mean and variance of this binomial distribution we learnt last episode. Then we need to find the new parameters that fit a normal distribution. So the mean and variance of this binomial random variable becomes our new normal parameters. So now we have successfully approximated the binomial distribution to a normal distribution. Now, there is a problem when attempting to approximate point probabilities. We know that the underlying binomial random variable x is discrete, so the point probability represents one entire column of the histogram. But when we approximate to a normal distribution, which is continuous, a point probability will always be equal to 0. Hence, we need to apply what is known as the continuity correction and instead find the probability between k minus 0.5 and k plus 0.5. This will ensure that we correctly approximate the whole column of the histogram. The central limit theorem is one of the most misunderstood theorems in statistics. Now let's first go through the context. In reality, we often have no idea what the underlying probability distribution of the population is, because it's hard for us to gather data for every single element. So we often take samples to get a better understanding of the population. But how can we make statistical conclusions of the entire population by just taking small samples? If we take samples from a population, then the distribution of these samples is called a sampling distribution. So the central limit theorem states that the mean of each of the samples will resemble a normal distribution. So in other words, the sampling distribution of the sample means will closely approximate a normal distribution. Are you mind blown yet? This is crazy because the underlying distribution can be unknown and it doesn't even have to be normal. But if we take samples with a large enough sample size, then the sample means will always follow a normal distribution. There is one important condition we have to remember. If we don't know what the underlying population distribution is, then we must have a large sample size n for the CLT to hold. However, if we do know that the original population distribution is already normal, then we can get away with a smaller sample size. A commonly accepted sample size is n greater than 30. The confusion occurs because the number of samples you take has nothing to do with whether or not the CLT will hold. The sampling distribution of the sample mean being normal is purely dependent on a large sample size. For example, the CLT will still hold if we only had one sample with a large sample size. However, visually, you can't really tell whether this follows a normal distribution because there is only one data point. But once we run many samples, then we also start to visually observe that it's a normal distribution and confirm the CLT. Okay, so let's visualize the CLT with an example. Say we have a random variable x with this weird PMF. As you can observe, this distribution is non-normal, so let's take a random sample but with size 30. Then we record the sample mean and plot this one sample on a sampling distribution. But we can't really tell that this follows a normal distribution, but we know deep down by CLT it really does. So let's take some more samples and again record each sample mean and plot them on the distribution. As we record more and more sample means, we can now also visually notice that the sampling distribution approaches normality. In many practical examples, we are often interested in estimating the proportion of a population with a specific characteristic. So we are more keenly interested in the probability of success P rather than the actual number of successes X. For example, in elections, politicians are interested in the proportion of votes they received rather than how many people that represents. Or Edison is interested in the proportion of defective light bulbs from his factory rather than the actual number. So let X be the number of successes in a sample, which means X will be binomially distributed. The sample proportion P hat is defined as this because it's just equal to the number of successes in the sample out of the total sample size, n. So P hat is another random variable that records the probability of success of a sample. Now by the CLT, the sampling distribution of the sample proportions this time will also be normally distributed with mean P and variance PQ on n. So let's end with a classic question. We're back at Edison's light bulb factory and Edison claims that only 10% of his light bulbs are defective. We, as curious statisticians, want to fact check his claim. We manually check 200 light bulbs and find 29 to be defective. Number 1. Calculate the sample proportion. We found 29 defective light bulbs in our sample of 200, hence P hat is 12%. Number 2. Specify the sampling distribution. Since the sample size is large enough at 200, we can apply the CLT. Hence, the sampling proportions will be normally distributed with mean P and variance PQ on n. Number 3. Comment on Edison's claim. Now, let's find out how our sample compares relative to our sampling distribution. So, what is our probability that our sample proportion is less than 0.12? As the sampling distribution is normal, we can standardize the score to calculate a z-score. Then we look up this z-score in a z-table to find the CDF value. Hence, the sample we observe is in the 98th percentile of the sampling distribution, and only 2% of the samples will have a higher sample proportion than what we observed. This makes it pretty unlikely that Edison was telling the truth, and the probability of defect is likely higher than 10%. So that's it for episode number 7. We explored through normal approximations, the central limit theorem, and sample proportions. And that's it on our series on statistics. Click here to watch episode 0 to remind yourself on the big picture of statistics. And I hope you enjoyed this series and it helped in some way to conquer the realm of statistics. So like, subscribe, and leave a comment down below on what you would like to learn in the future. I'll be there.